Determine the required magnitude of F1, F2, and F3 so that the resultant couple moment is this resultant. Okay, so all of this, it can be treated as a rigid body. The handles, everything, it's all rigidly connected together. Remember what rigid means, that after the forces are applied, there's the deflection is minimal or is negligible. In terms of, like, if you imagine that this was like all rubber and you put these big forces on it, the directions of these forces would change, everything would change. And so but it's not like you can't, the principle of couple moments wouldn't apply if it wasn't a rigid body. Remember how we derived the idea of couple moments and the couple moments being a free vector? That had nothing to do with the body. It's just that if this was rubber, all rubber, and you had these big forces on it, well, once you apply the forces and everything twists, well, how do you know that once the forces are applied, these are still in the same plane? Maybe this isn't a couple anymore, or it can't be assumed to be a couple. Maybe the couple axis has changed. It's a totally different problem. But if you knew the exact deflected shape and you knew the positions of all the forces, you could still apply the idea of the couple moments being a free vector. It would work, but just trying to give you a sense of the idea of a rigid body. Okay, but what we want to do is we take all of these couple moments, represent them as vectors, and they're free vectors. Just sum them all together, and that the net resultant couple moment is going to be it's like the net couple effect on this entire rigid body. So if we sum all of these couple moments as vectors, we want to get this net resultant vector. Okay, so let's start with this. What is the couple moment from the force F1? The moment vector. Well, we can see that it's going to be in the y direction, along the direction of the y-axis. That's going to be the moment direction, the moment vector direction. Now, positive or negative? Well, put your right hand, put the curl of the fingers in the direction of rotation. It's going to be in the negative y direction. So this is negative 0.2 F1 j hat. Okay, M2, this moment vector, this couple vector is going to be in the x direction. So, but positive or negative? Direction of rotation, put the curl of the right hand, the curl of the fingers of the right hand in the direction of rotation. It's going to be positive I hat. Okay. M3, the moment vector is going to be in the k hat direction. Negative k hat. Okay, now M4 is a little confusing. You might look at this and think that the moment vector is in the I hat direction, but this is directed at an angle here. You can see it goes 0.2, 0.2. So this line here is at 45 degrees. So what you have is, if we look down at this, here's y, and then this is negative x. This is at 45 degrees, and then the handle is going to be perpendicular to this. And this distance here is, we can see, so this 30 degrees, if we extend and then bring this is 30 degrees. So 0.3 cosine 30 is this dimension. So .26 meters. This is 45 degrees. Now we can use 0.26 times F4 and get the magnitude of the moment of the couple based on like that's the scalar definition of the couple moment, right? So just take this perpendicular distance from the two couple forces times the magnitude of the couple force. But then but we still need to represent it as a moment vector. So, I mean, we could do r cross f, but let's just do this manually. What is this as a unit vector? This direction. So we've got that would be minus cosine of 45 I hat plus cosine of 45 j hat. So, okay. M4, the magnitude of M4 is 0.26 times 150. Well, this times 150. 39. Okay, but M4 as a vector is 39 times minus cosine of 45 I hat plus cosine of 45 j hat. So minus 27.6 I hat plus 27.6 j hat. Oh wait, no, hold on. We can't just say that. That's the unit vector in this direction, but let's look at what is that, what direction is the unit vector? We have to look at this ourselves. So put the curl of the fingers in the direction of rotation of that F4 is creating of the right hand. So it's pointing in this direction. So this is the opposite. We've got, this is positive and this is negative. There we go. Okay. So that is the M1, M2, M3, and M4. And what we want is, these are free vectors, right? So just M1 plus M2 plus M3 plus M4 vector sum needs to equal this. So what do we have? Let's put all the I hats together. So 0.2 F2 plus 27.6 I hat. Now let's bring all the j hats together. Minus 0.2 F1 minus 27.6 j hat plus minus 0.2 F3 k hat. And then this is equal to 50 I hat minus 45 j hat minus 20 k hat. There we go. So now just set this equal to this equal to this equal to this, and solve for the F1, F2, and F3. So 0.2 F2 plus 27.6 is equal to 50. So F2 is equal to 50 minus 27.6 divided by 0.2 is 112 newtons. So that's F2. Okay, now minus 0.2 F1 minus 27.6 is equal to minus 45. So F1 is equal to minus 45 plus 27.6 divided by minus 0.2, 87 newtons. Okay, now minus 0.2 F3 is equal to minus 20. $100 newtons. There we go.